for problem number 8, the circuit has 2 switches and they are attached in parallel to the battery. In the first scenario, switch 1 is closed and switch 2 is open. So that allows the 1 microfarad capacitor to fully charge. So that means that it's going to gain the full voltage of the battery. Determine the magnitude and sign of the charge on each plate of the microfarad capacitor. So in this problem, let me make some space. So we've got the charge, which is Q. The equation for Q is capacitance times voltage, and we just multiply our 3,000 times 1 microfarad, which is 1 times 10 to the 6. That gives us 0.003 coulombs. Oops, that's a C. So that's actually the charge on each plate of the capacitor. And because I've got the positive going to this plate, that's going to give me the positive 0.003 coulombs of charge, and here I'm going to have this negative 0.003 coulombs of charge. The next step is to determine the electric energy stored in the 1 microfarad capacitor. There's many equations for the the energy of a capacitor. The one I use is 1/2 CV squared because I have it memorized, and so I get 1/2 1 times 10 to the negative 6 times the voltage of 3,000 squared, and that gives me 4.5 joules of energy. All right, in the next question, we have S1 open and afterward S2 is closed. So we are connecting the 1 microfarad capacitor to the resistor and the 3 microfarad capacitor, which is uncharged. So this is, first we're going to find the current in the circuit after the switch is closed, and the scenario here is that we no longer have this current, but we actually, and let me actually even erase this guy. We have a current that is built up on the positive side that is now going to run through the capacitor. And then this obviously is going to build up charge. So that's going to basically complete our circuit. We're going to say the current runs in this direction when S2 is closed, and right off the bat, immediately after the charge, we don't have any charge buildup on the 3 microfarad capacitor, so we can assume that there is no resistance from that capacitor, just the resistance from the resistor. So in this scenario, we're going to use our equation. I'm going to do the work for C up here. I is equal to voltage over resistance. The full voltage that was built up on the capacitor is going to go through the resistor, and that's going to be 3,000 over a resistance of 1.5 times 10 to the 6, and that gives me 0.002 amps. And then now we've reached equilibrium, so let's get rid of all this. Determine the charge on each plate of the 3 microfarad capacitor. So this goes to problem C. Let's do D over here. This one is going to be a long one, so I'm going to need some extra space. The first thing we know is in order to reach equilibrium, we have to have a voltage drop, and this is a new voltage drop, delta V1 and delta V2, that is equal. So we no longer have the 3,000 volts. We've reached equilibrium to make those equal values. So we don't know what they are yet, but we do know that voltage is equal to charge over capacitor. So if we just set the charge over capacitor for each one equal to each other, we also know that the total charge given by the first capacitor initially is 0.003, and then the total charge is also going to equal to charge 1 plus charge 2 because of conservation of charge. So I am going to use that substitution to solve for one of the charges, and then once I get that answer, I can solve for the other. So Q2 is equal to Q total minus Q1. I'm going to make that substitution in here. Q1 over C1 is equal to Q total minus Q1 over C2. And I'm going to go through the math of this and plug in the values in the very end. So I'm going to go through this quickly. Hopefully you can follow along pretty easily, and we also did this in class, so it's just a review. This should be C total. Going fast makes me mess up, so bear with me. Okay, so here we've got our final equation. You're going to plug in your values. Total 0.003. C1 is 1 microfarad. Don't have room, so I'm not going to write it out. And then when I add C1 and C2, I end up with 4 microfarads. And Q1 ends up becoming 7.5 times 10 to the negative 4. I'm going to subtract that from the total, so 0.003 minus 7.5 times 10 to the negative 4. And I get Q2 is equal to 0.00225 coulombs. So these are my charges on each capacitor. Last step is to find the energy dissipated in the resistor. The way you do that, we take the total energy when we had the 3,000 volts in just the 1 microfarad, and we subtract it from the total voltage when it splits between the two capacitors and it reaches equilibrium. So this one is the change in energy, which is U final minus U initial. My U initial is equal to 1/2 CV squared, which in this case was 1 microfarad times 3,000 squared, and that gave me 4.5. Oh, actually, I already calculated that, so you don't have to redo that. That was from part B. And then the U final was 1/2, 1 times 10 to the negative 6, and we need to figure out what the voltage is now that we've split the charges. So voltage is equal to charge over capacitance. I can just choose one, 7.5 times 10 to the negative 4 over 1 times 10 to the negative 6. That voltage will give me 750 volts. And because these are the same, I could do the calculation for Q2 over C2, and I should also get 750. So I'm going to do that. I'm going to add the two capacitors together. This one's 3 times 10 to the negative 6 times 750 squared, and it actually simplifies down to just adding these capacitors and then plugging it into the energy equation, and that gives me 1.125 joules. I still need to see how the energy changes, so I'm going to take the 1.125 and subtract it from 4.5, you're going to notice it's a negative, and that's because it's energy lost. So this is going to be energy lost through the resistor.